Hi everyone, thanks for joining. So in this series of lectures we're going to talk about choosing the right statistical tests depending on which types of data you have. So this first term that you see here in the second bullet is the so-called bivariate analyses or bivariate analysis. So that's where you have one y, which is typically denotes the dependent variable, and one x, which typically denotes the independent variable. So the reason for that terminology, the reason that we say y is a dependent variable, is because we assume that it depends on the different values of x. Okay. Another term that you may run across is this so-called multivariable analysis, and that's typically where you have one dependent variable, but you may have many independent variables or predictors. And then finally, multivariate analysis. So this means you have many dependent variables, y, so you could have a couple or more, and one or more independent variables, x. So there's a lot of confusion, and even in manuscripts, clinical manuscripts, and even statistical manuscripts, people get these two confused, but they actually mean different things. So multivariate means you have multiple dependent variables, and multivariable means you have one dependent variable but potentially multiple independent variables. Okay, so let's take this away. Alright, so just to recap from the previous lecture, most of the time when we're doing this hypothesis testing, we start out by believing that nothing's going on, and we're going to retain this belief until there's evidence or data suggesting otherwise. Okay, so if you remember, some of the typical types of things that we were looking at for null hypotheses were there's no difference between group means. So remember, we used the t-tests in that situation. Or there's no difference between proportions in say two groups, and in that situation we looked at comparing the proportions between two groups, and we used the z-test. It turns out that that's actually equivalent to the chi-square test, which covers the most general cases where you have potentially more than two levels for each of your variables. And so the chi-square test is actually what we'll use from now on. Another type of null hypothesis is that there are no relationship between two variables. Okay, and then over here on the other side for your alternatives is you'll basically see the opposites of those statements. So the first one would be that there is a difference between group means. So it could be mean systolic blood pressure in a treatment and a control group. For the proportion, there is a difference between proportions. So that would be an alternative. Or for the third one, there is a relationship between two variables. Okay, and if we were to actually write these in a little bit more rigorous way, you would see statements like this. So H naught, the mean in group 1, is equal to the mean in group 2, versus that they're not equal to each other. Or if we're talking about proportions, H naught would be that the proportion of events in group 1 is equal to the proportion of events in group 2, versus that those proportions are not equal to each other. And then finally, just a general statement, just a general H naught, that there's no relationship between x and y, versus that there is a relationship between x and y. And if you recall from last time, how we actually carry out this decision-making process is that, let's just say if our significance level is 0.05, which it commonly is for medical studies and in the medical literature, then we would actually retain our belief, so we wouldn't switch our belief in H naught if our p-value were greater than our significance level of, say, 0.05. On the other hand, if our p-value is less than 0.05, we would reject H naught and go in favor of the alternative. Okay, so remember, small p-values are evidence against the null hypothesis. in favor of the alternative, because that's how p-value probabilities are accumulated. They're evidence in favor of the alternative. Okay, this is a pretty useful slide, and we're going to talk about some of these different situations here, but essentially what you have is in this, so going this way, in these cells you'll see the different types of y variable that you can possibly have. So the first one is continuous, ordinal, binary, or nominal. Remember, you need to remember what those different kinds of variables are. We talked about those a couple lectures ago. Okay, so this arrow or these entries denote which type of variable your dependent variable is, and then down here at the bottom we have which type of variable our independent variable or our x variable is. So again, continuous, ordinal, binary, and nominal. Okay, so let's take these away, and inside the tables you'll see certain types of tests that are appropriate in those situations. So for instance, if your x variable is continuous and your y variable is also continuous, you may want to consider a correlation or linear regression. Okay, we're going to talk about both of those in a couple slides, actually in the next lecture. If let's just say your dependent variable y was binary, so you're interested in an event, so a yes or a no. That could be disease versus not. And let's just say your x variable or your independent variable is also binary, so that could be group 1 or group 2. Then you would do a chi-square test, or if your assumptions aren't met, and most software will tell you whether or not those assumptions are met, it has to do with the expected counts inside particular cells, then you could go with the Fisher's exact test. So most advanced software nowadays will give you a warning if the assumptions for the chi-square test aren't met, and that deals with the sample size and the expected counts within each cell. So you could alternatively do the Fisher's exact test in that case. Okay, and what I have here in parentheses is whether or not you're talking about paired data. Okay, so pre versus post. Remember, if we have groups where we're doing pre versus post, that means we're measuring the same individuals twice, or in each of the different treatment groups. So in that case, you would do this so-called McNemar's test. Okay, remember what we did if we were. Let's take this away. Remember what we said we would do if we were in this paired, where we had paired data, but we were looking at continuous types of dependent variables. So for instance, we were interested in looking at the systolic blood pressure levels between pre and post treatment. So in that situation we would do paired t-tests. So that's why I have parentheses here. So the parentheses here for this paired should correspond in the entry of the table to where I have parentheses as well. See here and here. And also for these non-parametric ones. Okay. Let's take this away. We're also going to look at what to do when you have a continuous dependent variable y and you have more than 2 groups. So that would mean that your independent variable, your x variable, is nominal with more than 2 different categories. Okay, so in that situation we're going to do an ANOVA, or if our assumptions for normality aren't met. So for instance, if our data is too skewed in one of the groups, or if we're dealing with ordinal, an ordinal type of response variable, then we would go with the non-parametric alternative to ANOVA, so Kruskal-Wallis test. Okay. This is also true in the situation here. So if we had continuous data, so we had continuous y variable and we had 2 groups, if our data were too skewed so it didn't really look normal, or if we had an ordinal y variable, we would also prefer the non-parametric tests instead of these t-tests. So in that situation, we would use the Mann-Whitney U. It's also referred to as the Wilcoxon rank sum because two different groups kind of independently discovered these non-parametric tests. So if the assumptions for the t-test aren't met, these non-parametric tests should be used. And then you'll also see, as I've mentioned before, there are paired versions, so paired versions of these non-parametric tests as well. So let's look at some examples. And in this set of slides, we're going to look at what should we do when X is categorical, and then in the next video, we're going to look at what should we do when X is continuous. Those are pretty much your most common types of situations. Okay, so if X is categorical, that essentially means you're comparing some characteristics, some type of outcome or response between two or more groups. Alright, so if Y is also categorical, so for instance, you could be interested in the proportion of hypertensive subjects in two groups. So your variable would be hypertension, and the value that it could take would be either yes or no. This is just there are different levels of hypertension, but for simplicity, let's just look at a yes or no type of hypertension. Okay, so in that situation, as we've seen before, we would usually be interested in comparing whether the proportion of this event is different among the different groups of our dependent variable X. Alright, so the chi-square test is the most appropriate test to use for that kind of data, unless some of your assumptions aren't met. And like I've said on the previous slide, usually the software will complain and say you have less than an expected number of 5 in this cell or in 50% of the cell. So in that case, the statistical software will usually prompt you to use this so-called Fisher's exact test. Alright. Okay, well, what if the outcome Y is continuous? So you've got a continuous dependent variable, and you're interested in comparing this thing across different groups of X. Okay, so a lot of times, most of the time, the comparison is going to be looking at whether the mean of this response is different among these different levels of X. So if you've got two groups, this boils down to this t-test that we've looked at in the previous lecture. If you've got more than two groups, this will be an ANOVA, and this ANOVA is an overall test. Okay, and it tests the overall mean. So for an ANOVA, your null hypothesis looks something like this: mu1 is equal to mu2 is equal to mu3 is equal to ... however many different groups you have. Let's just say we've got k different groups, versus an alternative that looks something like this. Well, at least one of these means, at least one mean is different. So the ANOVA test starts out with an overall test. So it tests the overall test of equality of all means. And if you were to reject this, then you could go in and do post hoc analyses and see exactly which means are different from each other. And we're going to look at an example of how would we carry that out. Alright, and in this last bullet I have, sometimes the data don't satisfy the normality assumptions, and those are necessary for the t-test and ANOVA to be valid. Okay, so that's why it's always good to plot your data first, look at a histogram of your Y variable in the different groups, and see if it looks like something's not normally distributed. So if there's a lot of skew, so if it's heavily skewed in one of the groups, or if your data is ordinal, then you should use non-parametric methods. Okay, and the Mann-Whitney U, sometimes this is referred to as Wilcoxon rank sum test, or the Kruskal-Wallis test if you have more than two levels of your X variable, are your non-parametric alternatives to the t-test and to ANOVA. So the Mann-Whitney U, or the Wilcoxon rank sum test as it's sometimes called, is the non-parametric alternative or the non-parametric equivalent to the t-test, to the two-sample t-test. The Kruskal-Wallis test is the non-parametric alternative to ANOVA. And for certain types of data, these should be used instead if the assumptions aren't met. And basically what these things wind up comparing are the medians instead of the means between groups. Okay. So here's some clinical scenarios, a research question, a clinical example, and the statistical test that you would want to do. So let's look at this first one. So the clinical example is, does the proportion of people who smoke differ between 50 to 65-year-olds with and without lung cancer? Okay, so it looks like we're interested in an event, so smoking status, and it looks like we're looking at 50 to 65-year-olds with, so that would be group 1, and without lung cancer. So we're interested in whether or not there's a difference in the proportion of people who smoke in those two different groups. So 50 to 65-year-olds with versus without lung cancer. Okay, so think about what kind of data this is. This is an event, smoke versus not, and our group levels, our X is categorical. Okay, so from the table that I've presented on a couple slides ago, you would want to do the chi-square test in this situation to test whether or not there's an association between your X and Y, or the Fisher's exact test if the assumptions aren't met. So if your expected frequency is less than 5 in too many cells, again, your software is going to complain and prompt you to use the Fisher's exact test instead of the chi-square, but they both test similar things. Alright, let's take this away. Alright, what about our next research question? So let's look at the clinical example first. Does mean forced expiratory volume differ between 50 to 65-year-old adults with and without lung cancer? So this FEV is a continuous measure. So our dependent variable here, let's think about what's going on. We have a dependent variable here that's continuous, and we're interested in a comparison between groups. So again, the groups are 50 to 65-year-old adults with versus without lung cancer. Okay, so let's think about it. Y is continuous, X is categorical, X has two levels, so we would be comparing two means to each other, and from the table we would want to carry out a two-sample t-test. Now if we collected the data and saw that the normality assumptions weren't met, so for instance these FEV levels were heavily skewed in one of the groups, then we would probably want to think about a non-parametric alternative. So the beauty of these non-parametric methods is that they don't make many assumptions. They definitely don't make the normality assumptions about your data that the t-tests make. Okay, but if the assumptions are somewhat met, you could use the two-sample t-test, or if you needed to, the non-parametric alternative, which would be the Mann-Whitney U, again sometimes called Wilcoxon rank sum test. Alright, let's take this away and let's look at the very last example here, and let's start with the clinical example first. So we would still be interested in this mean FEV and whether it differs among 50 to 60-year-old adults depending on stage of non-small cell lung cancer. So we've got 1, 2, 3A, 3B, and 4. Okay, so let's think about what kind of data we have here. We still have the same kind of continuous Y, or continuous dependent variable, but our independent variable has more than two levels. Okay, so in that case we would want to go with the ANOVA, and that would be an overall test of the means, whether the means are the same in all these groups. So whether the mean FEV level is the same in group 1, 2, 3A, 3B, and 4. And if we were to reject that overall test, we could dive in and do post hoc analysis and do pairwise comparisons to see actually which groups are different from each other. So let's take this away and move on. Okay, so let's look at an example where we actually carry out this calculation. So this is an example for the chi-square test. X and Y are both going to be categorical, and the question is, a physician wants to know if the proportion of male esophageal cancer patients diagnosed with multiple primary tumors differs from the proportion of female esophageal cancers with the same diagnosis. Okay, so our X variable is sex and male or female in this data set. Our categorical, so our Y variable is categorical, and it's whether or not the patient is diagnosed with multiple primary tumors or not. So they either have multiple primary tumors or they don't. So this is a yes or no. Okay. So naturally you will think, if you're thinking to yourself, okay, I've got a categorical X, I've got a categorical Y. If I want to study the association between these two variables, I should probably carry out the chi-square test, or if the software complains and says I don't meet the assumptions, I can do the Fisher's exact test. Okay, but let's do the chi-square test and see what comes out. To illustrate the chi-square test, we're going to look at a data set on esophageal cancer patients, and our outcome is going to be whether the esophageal cancer patient was diagnosed with multiple primary tumors, so multiple primary tumors versus not, so versus a single primary tumor. Okay, and the data set looks like this. The researchers got a sample of 60 male and 40 female esophageal cancer patients, and she records the number in each of these samples who are diagnosed with multiple primary tumors. So you have these individuals could be diagnosed with multiple primary tumors or just a single primary tumor. So you have this is a yes or no type of response. Okay, after the data is collected, it turns out that 40 men and 10 women were diagnosed with multiple primary tumors. Okay, so this is the 2x2 table that contains the data, and it's just the cross classification of the risk factor variable. So here sex and the disease variable, multiple primary tumors or not. Okay, and you'll see 40, just like in the last slide, were male and diagnosed with multiple primary tumors, and 10 females diagnosed with multiple primary tumors. And what you'll see here are the individual proportions in each of these groups. So this would be 40 in the male group divided by a total of 60, and this would be 10 in the female group divided by a total of 40. Alright, and what you see here are the corresponding 95% confidence intervals for these two proportions. So the question then is, do the proportion of multiple primary tumors differ between men and women with esophageal cancer? So in other words, is this 66.7% that we've observed in the males statistically different than the 25% that we observed in the female group? So we can run the chi-square test on this, and if we actually calculate the chi-square statistic from this 2x2 table, it'll wind up being 16.67, and this will give us a p-value less than 0.0001. Okay, and this is actually compared to a chi-square test with 1 degree of freedom. And the reason that you have 1 degree of freedom for this particular statistic is because for the chi-square test in a contingency table, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So in our case, both our X and Y variable have 2 different levels. So this would be 2 minus 1, which is 1, times 2 minus 1 again, which is 1, and you would wind up with 1 degree of freedom. So if you have a contingency table that has more than 2 levels for one of your variables, then the degrees of freedom from the corresponding chi-square test is going to change. So you'll essentially be comparing this test statistic to a different chi-square distribution with different degrees of freedom. But in this case, for the canonical 2x2 table, the chi-square test is one that's compared to a chi-square with 1 degree of freedom. Okay, so that's where this p-value comes from. And it turns out that actually a value of 16.67 is quite large for this kind of chi-square distribution with 1 degree of freedom. So our p-value wound up being less than our significance level of 0.05, and so this implies that the proportions are likely different in the groups. So our conclusion would be that there is a significant difference between men and women in their proportion of esophageal cancer patients with multiple primary tumors. And if we go back and look at the actual numbers, it's clear that comparing 25% in the women to 66.7% in males, it's clear that males have a higher rate of diagnosis with multiple primary tumors compared to females. Okay, so that's what the chi-square test allows us to do, is actually make that decision. So if you'll remember, I could just remind you, the test that we're testing in this situation is that the proportion of multiple primary tumors diagnoses in males is equal to the proportion of multiple primary tumor diagnoses in females versus that they are not equal. So alternative, I'll just write that they're not equal. So we've just rejected this null hypothesis since our p-value was less than our significance level. And this is our conclusion, that not only are they different, but if we go back and look, that one's greater than the other, specifically greater in males. Alright, so that's an example of how you would run the chi-square test, and sometimes you'll see, quite often actually, that the strength of this association will be reported in terms of what's called an odds ratio, and you may have seen this in the previous lectures on epi, but if you were to compute the odds ratio for this 2x2 table, you would wind up with an odds ratio of 6. So that's clearly clinically significant in most situations. So most of the time, anything greater than an odds ratio of, say, 2 is going to be something that you might want to pay attention to. Okay, and if you look at the 95% confidence interval here for the odds ratio, you'll see it ranges from 2.5 to 14.7. Okay, and an odds ratio of 1 indicates that nothing's really going on. So an odds ratio of 1 would indicate that the odds of the event in one group is not different than the odds of the event in another group. Okay, but you see that 1's not contained in this confidence interval. So the null value, or the value that would signify no association, is not contained in this interval. So this interval, so this odds ratio interpretation is also in agreement with our analysis here. Okay, so we found that there was an association when we used the chi-square test with all these p-values, and eventually that led us to reject the null. And if we were to compute an odds ratio from this data and a corresponding 95% confidence interval here, we would also reach a similar conclusion, since the null value of 1 is not contained in this interval. So 1 is not in this 95% confidence interval for the odds ratio. Okay. Alright, well, what if our x is categorical like it was in the previous example, but our y is continuous? So we've kind of looked at this introduced some methods to look at these types of problems in the previous lecture. We're going to look at those again, and we're also going to extend to the case where we have more than two levels for our x variable. Okay, so for this particular study, researchers examined subjects with hypertension and healthy controls, and the primary outcome of interest is this so-called aortic stiffness index, which is a continuous measure, and it's calculated from the aortic diameter evaluated by M-mode echocardiography. And so the research question for this particular study was, does mean aortic stiffness index differ significantly between hypertensive subjects versus controls? Alright, so you can probably guess, as long as your data looks somewhat normal, you could go ahead and go with the t-test in order to test this association. So the two-sample t-test, because these guys, so hypertensive and controls, aren't paired. They're independent samples. So you don't have this aortic stiffness measure, this aortic stiffness index measured, say, pre and post. So these two groups are independent of each other. Okay? So you can guess that the two-sample t-test is probably a valid option to consider from the last lecture. And in fact, that's what we'll do. So this is the data from that study. And in the hypertensive group, we had 15 subjects. Our sample mean was 19.16, and our sample standard deviation was 5.29. In the control subjects, we had 30. Our sample mean was 9.53, and our sample standard deviation was 2.69. So these sample means are the sample means of this aortic stiffness index in each of these groups. Okay, so our question of interest then is, does mean aortic stiffness index differ between these two groups? If we wanted to write it down more formally, it would look something like this. So our null would be that the mean aortic stiffness index in hypertensive subjects, which I'm denoting here M sub H, is equal to the mean aortic stiffness in control subjects, versus the alternative, that there is a difference in the means. Okay? So the question then is this observed sample mean of 19.16 in the hypertensive subjects, does that indicate is that statistically different from 9.53 in the healthy subjects? Okay. So if we were to carry out the t-test, we would get a t-statistic that was equal to 6.63. And if you remember back a couple lectures ago, our degrees of freedom for this test would be degrees of freedom is equal to N1 plus N2 minus 2. So it would be 30. So it would be 15 plus 30 minus 2. And we would get 43. So this t-statistic that we've computed from the data, 6.63, if you compare that to a t-distribution with 43 degrees of freedom, you'll wind up with a p-value that looks something like this. So it's essentially smaller than 0.0001. Okay? And so we have a p-value less than 0.0001 that indicates this t-statistic that we've computed is extreme because it gave us a small p-value, and this is giving us information and leading us to a decision to reject. So our decision should be to reject H0. And our conclusion then would be that there is a significant difference in mean aortic stiffness index between hypertensive and healthy control groups. And to go further, So to make our interpretation even more meaningful, we would conclude that the mean aortic stiffness is larger or greater in hypertensive subjects compared to control subjects. Okay, so remember, once we make the decision to reject the null, if we've done a two-tailed test, we can then go back in the data and look and see what's the direction and magnitude of the differences. So that's what we've done here. We've gone back and looked at the actual sample means. So the sample mean in the hypertensive group was larger than the sample mean in the healthy group, healthy control group. Okay, so that's our interpretation. And this is what's on this slide, the next slide, more about this interpretation. So we've reported the difference in means, or we're going to report the difference in means and the corresponding confidence interval. Okay, so we've concluded that the mean aortic stiffness index is significantly greater in hypertensive subjects compared to controls. And if we were to actually compute that difference, the difference in means, we would wind up with this value, 9.63, and our confidence interval for that difference in means. So this is a 95% confidence interval for mu hypertensive minus mu control. Okay, so you see that the null value of 0 is not contained in this confidence interval for this difference. So since 0 is not contained, if you were to base your decision on the confidence interval, you would reach the same conclusions that we've reached with the formal t-test and p-value. Okay, so again, you see that the confidence interval is giving you a similar type of decision, since they're based on the same statistics as you would have gotten if you had done the t-test. Okay, so if we wanted to even go further, we could say that we are 95% confident that the true difference in means, so mu sub h minus mu sub c, is between the lower endpoint 7.31 and the upper endpoint. So we're 95% confident that the true difference in means is somewhere there. Alright, so I just want to point out that if we had have noticed that the aortic stiffness index in either of these groups were skewed, so if we had plotted the data for the subject, so the mean aortic stiffness index in the hypertensive groups and in the control groups, if we had looked at a histogram of the data in each of those groups and saw skewness, heavy skewness, or if RY were ordinal, then we should go with a non-parametric method instead of a t-test. Okay. Okay. So what if we have more than 2 sample means that we're interested in comparing? What if we had 3 groups, or 4 groups, or 5 groups? Well, one approach that you could think of would be to look at all the possible two-way comparisons, so all possible 2-sample t-tests among the different groups, and try to determine which means are different based on these pairwise tests. Well, the problem is if you do this, if you just blindly do all these pairwise comparisons, then at the end of the day, you're not controlling your type 1 error. So essentially, you have, just by the sheer number of hypothesis tests you would be doing, you're inflating your type 1 error. You're inflating your chance of saying that something is significantly different when in fact it really is not. Okay? So you can see, I have a table here, and this would be the number of different groups. This would be the number of comparisons that we would have to do if we were going to do all pairwise comparisons, and this is what happens to our type 1 error if we do that. So you can see that once you get down here in, say, 15 groups, if you have 15 different groups that you're comparing to each other, this essentially winds up being 105 comparisons, and you're almost guaranteed with near certainty to commit a type 1 error. Okay? And these arguments are easy to make just from the laws of probability and by the sheer number of comparisons that you have to do once you increase your number of groups. Okay? So if you have 3 groups, that winds up being 3 pairwise comparisons you would have to do. If you have 4 groups, that's 6 pairwise comparisons. If you had 6 groups, that would be 15 pairwise comparisons, or 6 choose 2. Okay, so the number of comparisons that you have to do grows, and so does your probability of committing a type 1 error. So that's really not the way to go, and this ANOVA is the way to go, and it allows you to do an overall test first to determine if any of the means are different, and then if you reject the null hypothesis in an ANOVA, then you can go and further refine and look at pairwise comparisons and try to identify which groups are different. Okay? So one way to do this is to run an ANOVA first. So you'd run an ANOVA first, and what you would wind up calculating is so-called F statistic. And so ANOVA relies on an F test to compare all these means at once. And after you run the F test or do an ANOVA, if you were to reject the null, so recall the null for an ANOVA looks like this, that the mean in group 1 is equal to the mean in group 2 is equal to the mean in all k groups. So if you were to reject this, then you know at least one of the means is different. That's the alternative for ANOVA. Okay, so if you were to reject, then there are certain ways that once you go to do your multiple comparisons, all your pairwise comparisons, that you can adjust and preserve your type 1 error. This is one of them. This is the Bivariate correction. So essentially it just divides your significance level by a certain number, and the certain number is the number of comparisons that you're going to do, and you would only reject if your p-value were less than this adjusted significance level. Okay, if you follow this Bivariate adjustment, then you are protecting your type 1 error rate. Okay, it can be conservative. There are other methods to adjust after an ANOVA is done. Probably one of the most popular ones is this so-called Tukey-Kramer method. So Tukey-Kramer. And it also is an adjustment for pairwise comparisons. So most statistical software will give you an option to do this Tukey-Kramer adjustment for multiple comparisons after an ANOVA is done. Alright, so let's actually look at an example. So remember, an ANOVA is when you have a categorical X with more than 2 levels and a continuous Y. So in this study, we're looking at serum lipid-bound salicylic acid, LSA, and we're trying to determine if it can be used for the detection of breast cancer. Okay. So actually we're not going to look at exactly how we can use this thing as a diagnostic, but we're going to do something that might seem natural to do as some kind of a preliminary type of analysis. So actually what we're going to do is we're going to see if the mean LSA is significantly different among the 4 different breast cancer groups that we're going to talk about here. So we're going to have a normal control group, a benign breast disease group, a primary breast cancer group, and a recurrent metastatic breast cancer group. So we're going to have 4 different groups. So 4 groups. And our question is, do these groups have different means? And if so, So if we were to reject an ANOVA, which ones are different? And of course we would want to control for multiple comparisons. Alright, so here's the breakdown of the data. So in the normal control group, had an N of 350. This was the mean LSA level, and this was its standard deviation. In the benign breast disease group, we had again 350. This was the mean LSA level and standard deviation. For primary breast cancer, 350. This was the mean LSA level, standard deviation. And for recurrent metastatic breast cancer, again 350. This was the mean LSA level and its standard deviation. So this is a summary of that data from that study. And if we were to conduct an ANOVA on this data, and we calculated our F statistic, so we would compute that from the data. You don't have to worry about the formulas, but understand that whatever software you're using is doing essentially a glorified t-test in the background for multiple groups. Okay, so you calculate an F statistic, and in this particular case it winds up being 330.3, which is quite large. And what you'll notice here is this is actually the distribution that this test statistic will be compared to in order to compute a p-value. So what is this guy? This guy is an F distribution with numerator degrees of freedom 3. So this is an F with numerator degrees of freedom 3 and denominator degrees of freedom 1396. So for the F distribution, we have actually two parameters. We have a numerator degrees of freedom and a denominator degrees of freedom. Okay? One of them deals with essentially how many groups we have, -1, and the other deals with the number of observations we have minus how many parameters we've estimated, essentially. Okay? Again, don't get carried away with too much detail about that. Our main goal here is for analysis via software and then correct interpretation and decision making. Okay, so if you were to, let's take this away. So if you were to run this test, calculate this, compare it to the correct F distribution, you would wind up with a p-value that's again small. Okay, it's less than our significance level of 0.05. So our conclusion here is that at least one mean is different. So at least one mean is not equal to the others. So we've rejected the null hypothesis for an ANOVA, which is that all the means are equal. Okay, so this is the null hypothesis that we've rejected, that the mean in the normal controls is equal to the mean LSA in benign breast disease, equal to the mean LSA value in primary breast cancer is equal to the mean LSA in recurrent metastatic breast cancer. Okay, so we've made a decision that at least one of them is different, one of those means is different, but which ones are different? Okay, so what we see here in this graph is a plot of LSA levels. So what you have is the mean in each of these groups and the corresponding confidence intervals. Okay, so the position here in the vertical direction is the actual mean value, and these diamond shapes, so here are the corresponding 95% confidence intervals. Okay, so you can probably kind of already get some intuition just by looking at this data that it looks like you have kind of a clustering of three different groups here. So it looks like the normal controls are clustering down here. Benign breast disease and primary breast cancer are somewhere here. And finally, recurrent metastatic breast cancer looks different from the rest. Okay, but how do we actually formally do that? Well, we can do this post hoc comparison. So we've got 4 groups. That leads to 6 comparisons that we have to do. Okay, so that would be 6 pairwise t-tests in this case, and we're going to do a Bivariate adjustment. Okay, so the Bivariate adjustment in this case, we would just adjust our significance level from 0.05 by dividing by the number of comparisons that we're going to do. So we're dividing by 6, and we get a new significance level of 0.00833. So if we want to call something significant, and we also want to preserve our overall type 1 error, then this would be what we should be comparing our p-values to. Okay, so let's go down here and look at all the 6 comparisons that we need to do. So recurrent metastatic breast cancer compared to primary breast cancer. This would be the difference in those means, so the difference in the mean LSA values, and a 95% confidence interval for that difference, and the unadjusted p-value from the t-test. So this value, we would compare it to our adjusted significance level of 0.00833, and we see that it's in fact less than that. Alright, if we follow that same logic, recurrent metastatic breast cancer compared to benign breast disease, this is the difference in means. This would be the 95% confidence interval for that difference, and this would be the corresponding t-test to compare those two means. So the mean LSA values in the recurrent metastatic breast cancer group to the benign breast disease group. Again, we would want to do the comparison to our adjusted significance level so that we maintain our type 1 error, and we see that this is also significant compared to this. Okay, so the other ones follow via similar arguments. This guy would be significant, this one would not. So this one wouldn't even be significant at a 0.05 level, but we want to compare it to our adjusted level. This one is significant, and this one is significant. Okay, so all the means are different from each other except for the benign breast disease and primary breast groups, and that's precisely what we saw if we go back on the slide here. So all the means are different from each other except these two. So graphically we saw this behavior, and this allowed us to actually formally say or make that decision. Okay, and the interpretation interpreting these results is going to be essentially the same as what we've done before. So this comparison gave you a positive difference in means, so you would conclude that the mean in the recurrent metastatic breast cancer group is larger than the mean LSA value in the primary breast cancer group, and so on and so forth. So that would be the interpretation. Okay, so just some things to point out. If your Y variable in one of the groups is too skewed, or if the Y variable is ordinal, then you should use a non-parametric test, which in this case the non-parametric alternative to ANOVA is this so-called Kruskal-Wallis test. Okay, and then after you do this Kruskal-Wallis test, there are multiple testing methods that you can perform on the data after you've done your Kruskal-Wallis test. For instance, if you reject the null hypothesis there, and you want to do your pairwise testing, your post hoc analysis. Okay. So in this lecture, we've seen that it's important to understand what data types you have so that you can perform the correct test. So that's always the case. You want to understand precisely what kind of data it is and what types of questions you can answer with the data, and you want to know exactly what types of hypotheses are you testing, what do they look like. Okay. In this lecture, we've looked at examples where X was categorical and Y was either dichotomous or continuous. Okay, categorical X variables are probably the most common and although in the next lecture we are gonna see, you know, what happens when X is continuous. But usually we're interested in looking at differences between groups. So that means your X is categorical. Okay. So in the next lecture we're going to discuss which test to use when our X variable is continuous. Thank you.